Good evening. Today we are continuing with Chapter 5. We are still on the topic of algebra basics, expressions, and polynomials, with today's focus being on the order of operations. We'll also take a look at the concept of absolute value and discuss algebraic expressions. To evaluate an expression correctly, you must follow the order of operations. So, for example, if you were to see a group of expressions involving several different operations, let's say addition, subtraction, and multiplication, your approach to calculation, in order to get the right answer, has to follow a prescribed or a predetermined order of mathematical operations. Um, so, in the scenario that I just mentioned, wherein you're looking at a set of grouped expressions involving addition, subtraction, and multiplication, then according to the established order of operations, you would have to begin with multiplication, then proceed with addition before you can subtract in order to arrive at the correct answer. Any other approach would give you the wrong answer, and we'll look at this in more detail as today's lesson progresses. If an expression uses more than one set of grouping symbols, start with the inside set and work outwards. This is also known as the FOIL method, and we'll see this being implemented in more detail in Lesson 11, which focuses on multiplying polynomials. Okay, so more practice questions starting on page 869. When a mathematical expression contains more than one operation, its value may depend on the order of operations. To avoid confusion, mathematicians have established a standardized approach to performing operations. In a nutshell, the order of operations always follows this flow. Start with expressions in parentheses or any other grouping symbols that enclose operations. Next, work on terms that have exponents and roots, then multiplication and division, working from left to right. And finally, complete any addition and subtraction operations, also working from left to right. There is a mnemonic that is helpful when remembering the flow of operations we just discussed, and it's known as PEMDAS. P stands for parentheses, E for exponents, M represents multiplication, D for division, A and S for addition and subtraction, respectively. And I got this graphic from mathresources.com. This example shows how to apply the order of operations. Notice that the parentheses are used in two places in the expression. However, only the first set of parentheses encloses an operation. The second encloses a signed number. So we're asked to evaluate the expression 5 plus 3 squared divided by 4 plus 3 times negative 1. You're going to start by performing the operation in parentheses. 5 plus 3 equals 8. Then raise 8 to the power of 2, which is 64. And according to the order of operations, we then divide 64 by 4, which gives 16. 3 times negative 1 is negative 3. And our final step, adding 16 to negative 3, gives us 13. So your calculator is programmed to recognize and follow the order of operations. When you're using your calculator and you're working with an expression similar to the example that we just completed, using parentheses will serve as an important guide to ensuring that you are actually following the correct order of operations. So as long as you enter your parentheses correctly, the calculator will follow the correct order of operations and will return the right answer. In more complicated expressions, one set of grouping symbols may be nested with another. To avoid confusion, you want to use brackets or braces to group operations. So here, going back to the previous example, we have 5 plus 3 squared divided by 4. So you want to put this entire expression in brackets. putting 5 plus 3 squared divided by 4 in brackets lets the calculator know that this entire expression has been grouped together as one term. And it allows it to follow the correct order of operations in your entry. So to evaluate an expression with more than one set of grouping symbols, you want to work from inside out, and we'll see an example of this in the next slide. So in this example, we're asked to evaluate the expression 4 multiplied by open brackets 5, open parentheses, -4 plus 3, close parentheses, plus 2, close brackets. So you want to start by performing the operations in the inner set of grouping symbols. -4 plus 3 equals -1. Then you want to proceed with the operations inside the brackets, since multiplication comes before addition in the order of operations. So you want to multiply 5 by -1, which gives -5. And then adding -5 to 2 gives -3. -3 times 4 is -12. So if you've noticed, we've worked from inside out. We've added -4 plus 3. We multiplied the result of that by 5, which gave us -5. And then adding -5 to 2 gave us -3. -3 times 4 is -12. Recognize that the division bar, also called a fraction bar, is a grouping symbol. So before you divide, you want to perform any operation shown above and below the bar. So here we're being asked to evaluate the expression 15 plus 25 divided by 2 times 5 plus 6. So you want to start by performing the operations above and below the fraction bar. 15 plus 25 is 40. 2 times 5 is 10. Then divide 40 by 10, which gives 4. 4 plus 6 is 10. We followed the order of operations in evaluating this expression, and we've arrived at the correct answer. Now on to lesson 5, which focuses on the concept of absolute value. The magnitude of a number without a sign is called the absolute value. Absolute value is used to determine the distance between 0 and a positive or negative value. When considering the order of operations, we want to treat absolute value symbols the same as we would treat a set of parentheses. Absolute value is denoted as two straight lines around a number, as illustrated here with -5, showing two straight lines around it. The absolute value of a number is its non-negative distance from the origin on the number line. Absolute value essentially establishes a distance from 0. So looking at the number line, +5 is exactly 5 singular units from 0. -5 is also 5 singular units from 0. In essence, the absolute value of -5 is 5, and the absolute value of +5 is also 5. In this example, we're being asked to identify the absolute value of a -13. Remember immediately that the absolute value of a number is its non-negative counterpart. So in other words, the absolute value of a number is never negative, and the only answer choice that correctly reflects this fact is the first one here. So you can safely say that the absolute value of -13 is +13, or just simply 13. As stated earlier, absolute value symbols are treated as parentheses when considering the order of operations. So if the numbers inside the absolute value sign show addition or subtraction, or even multiplication or division, you want to perform those operations first before you proceed. So in this example, we're being asked to evaluate -20 times the absolute value of 17 minus 34. I wrote out the steps for you in orange here so that you can follow along with the order of operations being performed. So treating our absolute value symbols as parentheses, 17 minus 34 is -17. So you want to make a mental note here that just because we treat absolute value symbols as parentheses does not mean that we ignore their mathematical implications. So we're still evaluating the absolute value of the term inside the absolute value symbols, So we've completed the subtraction. We've arrived at a negative value, negative 17. So the absolute value of negative 17 is positive 17. We then proceed by multiplying negative 20 by 17. So our final answer is negative 340. So here's a test. Here's a test tip for you. A signed number, whether positive or negative, is used to show the direction in relation to 0. However, when you see a number inside two straight lines, you're working with its distance from 0, which is always positive. So reiterating, signed numbers are an indication of directionality, or the direction of the number in relation to 0 when we're looking at the number line. On the other hand, the absolute value of the number signals or indicates its distance from 0, and that distance is always non-negative. The concept of absolute value often presents itself in real life situations. For example, if you were to write a check for $400, but your available balance is $314, your account will be overdrawn by $86, right? Your bank record would show a balance of negative $86. However, from a practical perspective, you would just simply state that you need $86 or that you're $86 short. So essentially, you're thinking in terms of absolute value or the magnitude of the overdraft amount without the negative sign. So on to lesson 6, which is about algebraic expressions. Algebraic expressions show mathematical relationships using numbers, symbols, and variables and letters that represent unknown numbers. Algebraic expressions denote numerical relationships by using a combination of variables, numbers, and mathematical operations. Variables are symbolic representations of unknown quantities or quantities that vary. Variables can be represented using letters, for example, x or y. Each time the same variable representation is present within an expression, the variable represents the same quantity. So for example, if you were given an expression 3xy plus 8x plus 9z, and you're told that x is equal to 2, then in your original expression, everywhere where you see x, just know that it can be replaced with the same quantity, which in this case would be 2. To solve algebraic expressions, change numerical relationships described in words to their algebraic equivalents. So here are a few examples of algebraic expressions translated into their symbolic representations. The product of 5 and a number can be rewritten as 5 times x. Why? Well, we don't have any information about what the unknown number is. It could be 100, it could be 45, negative 75, or even 0. In other words, it can vary, and as a result, we have leeway to represent this unknown quantity as a symbol. In this case, the author has chosen x, so the product of 5 and a number can be rewritten in symbolic form as simply 5x. A number decreased by 12 can be rewritten as x minus 12. Again, the idea is that we have no information about the number, we just know that it decreases by 12. So we can represent the unknown number or the unknown quantity as x and restate the expression as x minus 12. So note that x can take on any singular value. So let's say that we have predetermined that x equals 100. In this case, 100 minus 12 would give us 88. Or x could represent a term. So for example, we could have 100 minus 20 divided by 5, and the entire term, 100 minus 20 divided by 5, could be represented by x, knowing that no matter what is on the left side of operation here, which in this case is subtraction. So no matter if it's a single value like 100, or if it's a more complex term like 100 minus 20 divided by 5, we know that that value or that term will always decrease by 12. Or we can just simply rewrite the expression as x minus 12. The sum of 3 and the square of a number can be written as 3 plus x squared. 6 less than the quotient of a number and 2. So let's think through this carefully. You remember from our earlier lessons on division, we know that a quotient is the resultant number from a division operation, right? So here we're told that the quotient comes from a number. What number? We don't know. It's a variable, so we can represent it with x. So the quotient comes from some unknown number and 2. So this can be rewritten as x over 2 or x divided by 2. We're also informed that the quotient is 6 less. In other words, 6 is being subtracted from the quotient, and the quotient is derived by dividing some unknown quantity by 2. So we can rewrite this expression simply as x over 2 minus 6. 1/2 of a number increased by 15. Again, just thinking through the information that we're given here. 1/2 of a number, what number we don't know, so we can just represent that unknown number or quantity simply as x. We're also told that this unknown number, once it's been halved or divided by 2, then increases by 15. So symbolically, we can represent that as 1/2 times x, or half of x, or simply x over 2, plus 15. 4 times the difference of -3 and a number. So whatever this unknown number is, we know that it's being subtracted from -3. And that difference, remember, a difference is the outcome of subtraction. Here, the difference of a -3 and a number simply means that when you subtract -3 from an unknown number, let's call it x, what you get from that operation, or the outcome of that operation, is the difference. And that difference is being multiplied by 4. So you want to make sure that you're capturing the expression that represents the subtraction operation that yields your difference by putting -3 minus x in parentheses. And we also know from the statement that the difference term here is being multiplied by 4. So we can rewrite this entire expression as 4, open parentheses, -3 minus x, close parentheses. A number less another number. So here we're dealing with two unknowns being subtracted from each other. We can represent the first unknown as x and let the second unknown be y. And so this algebraically can be rewritten as x minus y. So in this next example, we're given information about 10 less than the square root of the sum of a number and 3. You want to start by isolating the number or variable, and then also the operation that's mentioned first. So two things you want to isolate first, either the number or the variable and the corresponding operation. So here, 10 is the first number mentioned. Less, indicating subtraction, is the first operation mentioned. So we know that we are subtracting 10 from the square root of the sum of a number and 3. What is the number? We don't know, but we can represent it symbolically as x. We do know, however, that this unknown number needs to be added to 3, after which point we need to then take its square root and subtract the result from 10. So we rewrite this symbolically as 10 minus the square root of x plus 3. Note that to do well in the algebra portion of the mathematical reasoning test, you must be able to rewrite real-world situations or scenarios as mathematical expressions. It is necessary for you to develop a skill so that you can write equations and functions, apply formulas as necessary, and even solve word problems that will be part of your test. To check whether the expression you have chosen is correct, substitute easy numbers into the expression and then complete the operations, remembering to follow the established order of operations or remembering the PEMDAS order. Then you want to check to see whether or not the answer you derived is a reasonable one based on the situation that you're assessing in the question. So in this example, we're told that Kyle processes sales for an online bookstore. The shipping and handling on an order is equal to 4% of the total cost of the order, plus 95 cents per book. If C represents total cost in dollars and N represents the number of books in an order, which of the following expressions could be used to find the price of shipping and handling for an order? This kind of problem is called a setup problem, so you need to recognize the correct way to find the algebraic expression representing the price of shipping and handling based on the total cost and the number of items being shipped. So we're told that shipping and handling represents 4% of the total cost and that the total cost is represented by C. So from our lesson on decimals, we know that the decimal equivalent of 4% is 0.04. We also know that the word of signals multiplication. So 4% of the total cost can be written as 0.04 times C. We're also told in the problem that the percentage of the total cost is added to the charge per book. So 95 cents is the charge, and we're told to use N to represent the number of books. So if you were sending one book, you would multiply 0.95 rather by 1, and if you were sending 2, you would multiply 0.95 by 2, and so on. So since we don't know how many books are being sent, we need an expression representing this portion of our algebraic equation, right? So we can simply let x represent the unknown number of books that will be multiplied by 95 cents. In other words, 0.95 times x, or simply 0.95x. So we haven't forgotten that we need to account for the total cost, and we've already predetermined or established that that expression can be represented by 0.04 times C or 0.04C. So to accurately represent our complete shipping and handling equation, we go back to the question where we're told that the shipping and handling on an order is equal to 4% of the total cost of the order plus 95 cents per book. That signals to us that we need to add the expression representing the percentage of the total cost, which is 0.04C. So we need to add 0.04C to the expression representing the price per book, which we've already established is 0.95 times N. So in other words, our shipping and handling expression should represent the percentage of the total cost plus the price per book. Option 3, 0.04C plus 0.95N captures the correct algebraic expression for the scenario. In terms of simplifying and evaluating expressions, simplifying an expression just means that you want to perform all the operations that you can within a particular expression. So when you're working with variables, you need to remember an important rule, which is that you can add or subtract like terms only. A term is a number or a variable or a product or a quotient of numbers and variables. So a term cannot include a sum or a difference. And x over 2, for example, represents a term, would produce a quotient once 2 is divided into whatever value x takes on. 3x is a product, so this 3x by itself is a term. 9 is a term because it's a number. So again, based on our definition, a term is a number, a variable. Here's a variable on its own, y, a product, so 3x, 5y, those are terms. Or a quotient, x over 2. And I included z squared as well, because this is also an example of a term that you'll see quite often, a variable raised to a certain power, in this case 2. Like terms have the same variable and they're raised to the same power. So for example, 3x squared and 5x squared are examples of like terms because they both have x as a variable and both variables are raised to the power of 2. And they also both have a whole number written before the variable. So 3x squared and 5x squared are considered like terms. 8y and 4y are like terms because they both have a number written before the variable and they both share the same variable y. However, 6x squared and 6x and 2x squared are not like terms because the variables are not raised to the same power. In this case, when you see a variable written on its own, the assumption is that it's raised to the power of 1, but for the sake of this lesson, we just know that one term has a squared, or the other term has, well, is technically raised to the power of 1, but that's not mentioned in the book. So we'll just simply say that 6x is different from 2x squared, okay, in this particular example, because they both have the variables have different powers. To simplify an expression, you want to combine like terms. So I went in with a little bit of color to make it easier to see the like terms. Let me zoom in. So here we're being asked to simplify 2x minus 5 plus 4x squared minus 8 plus 6x. So in this example, what you want to do is start by grouping your like terms. In orange here are 2x and 6x, our first pair of like terms. Next, we have 5 and 8. Those are our whole numbers with no variables written next to them. So we group 5 and 8. And then 4x squared is our third term. In this case, we have three groupings. We have this 2x plus 6, that's our first. We have -5 and -8, which is our second term, and or second grouping, rather, second grouping of terms. And then we have 4x squared, which is our third term. And if you notice, you want to make sure that you're keeping the signs next to your terms. So our whole number here is a -5. So when you're doing your grouping, you want to make sure that you're including that negative sign in your parentheses. Same with 8. You want to make sure that you're including the negative sign here. So to continue with our simplification, we know that we're adding together 2x plus 6x because those are like terms. That gives us 8x. And then we're also adding together a -5 plus -8, and that gives us -13. And then we have 4x squared, which is simply write down 4x squared because it's the only term that appears with a whole number and a variable squared. So then you just rearrange the terms to write the term with the greatest exponent or the greatest power first. In this case, it's 4x squared, then 8x. And so there's nothing written, there's no sign in front of 8x, so that indicates that it's positive. So you would write 4x squared plus 8x minus 13. And we know that this positive sign is written right next to -13. That indicates multiplication, or you could consider this as multiplying by a positive 1. And that would give you -13. And that's a distributive property that we'll see later on in this lesson. What happened here with this plus and minus is something known as a distributive property, where you imagine that there's a 1 here and you're multiplying a positive 1 by -13, and that gives you -13. Okay. And so that's this same expression that we're given in simplified form would be written as 4x squared plus 8x minus 13. And that's simply because we have one term that's being squared, right, 4x squared, and then we have two like terms, 2x and 6x. So if we add those together, we get 8x, and then we have two whole numbers, a -5 and a -8. You get -13. And so this is just a simpler way of representing this entire expression. And so, yeah, that was the goal of this particular exercise, was just to simplify this very long expression and write it in a more condensed form, which we've done right here, okay, with 4x squared plus 8x minus 13. So the distributive property that I mentioned earlier is the next portion of this lesson. And this allows you to remove grouping symbols to simplify expressions. And we can state the distributive property using symbols. So for example, when you see A parentheses B plus C, that can be written as AB plus AC. Why? Because we already know from our previous lessons that when you see two terms written to two variables or two numbers written close together like this, that implies multiplication. And when you have parentheses, it means that this particular variable is being multiplied into everything in the parentheses. That's why it's written together like this, right? So A, and then in parentheses B plus C essentially means that we're multiplying A times B plus A times C. Okay, and that's essentially what the distributive property means or tries to convey, is that whatever is written outside of the parentheses is distributed across everything in your parentheses. Also, the same is true if the operation is subtraction. It doesn't matter what the operation is, right? So in this case, it's subtraction. A and then open parentheses, B minus C, close parentheses, redistributes to AB, A times B, minus AC, or A times C. Okay, if in parentheses we had B over C, B divided by C, it would redistribute to AB divided by AC. Okay, so again, anytime you see a term or a variable outside of parentheses, know immediately that the distributive property applies, and you would just multiply everything with inside the parentheses by whatever is outside of it. Each term inside the parentheses is multiplied by the term outside the parentheses, and the results are added or subtracted depending on the operation inside the parentheses. So in this particular instance, we're adding because the operation inside the parentheses is addition. In this example, we're subtracting because the operation inside the parentheses is subtraction. So the next example gives us something to work with in terms of distributive properties. Okay, in this example, we're being told to simplify 4x minus 3x open parentheses, minus 3 open parentheses x plus 9 close parentheses plus 15. So you want to use the distributive property and multiply 3 by each term in the parentheses. And we're going to do that because, again, according to our order of our operation, PEMDAS, we're going to start with parentheses first. So you multiply negative 3 by x, and you would get negative 3x. And then negative 3 times 9 is negative 27, which is this step right here. And then you want to group your terms, right? So we have 4x from this step by multiplying negative 3 by x, we have negative 3x. So that those are our first pair of like terms. And then we are left over with whole numbers, a negative 27, which we got from negative 3 times 9, and 15, which comes from this term right here. So 4x plus negative 3x is simply just x. And then negative 27 plus 15 is negative 12. So our answer is x minus 12. So evaluating an expression means finding its value. To evaluate an expression, you want to substitute a given number for each variable. So again, you would follow the order of operations. So in this example, we're told to evaluate the expression 3x plus 2y over 4 when x equals 6 and y equals 5. So you simply would replace your variables with the numbers that you're given. So here we're told that x equals 6. So you would go back to your expression. As you rewrite it, everywhere where you see x, in this case, we only have one x, so we're going to replace x with 6. If this expression was continuing and there was like 9x plus 10x plus 4, everywhere where you saw x, you would just replace x with 6, okay? Same thing with y. We're going to go back to our expression and we're going to replace y with 5. So we only have one term, I should say, with y, that's 2y right here, and so you would replace that with 5. And then again, going back to our order of operations, we know that with the division, we have to work on everything above first and then go to whatever is below, right? So 3 times 6 is 18, 2 times 5 is 10, 18 plus 10 is 28. So we have our numerator, and then our denominator is 4, and we would simply divide 28 by 4, and that gives us 7. And again, here it's important to pay attention to the order of operations, because if you had done 3 times 6 is 18, and then you try to divide by 4, you would get like 4 times 4 is 16 with 2 left over. And then 4 into 10, you would get 4 times 2 is 8, you would get 2 with 2 left over. That's not the right answer, right? The right answer is 7. So it's important to pay attention once you've replaced all your variables with whatever numbers, or you've grouped your like terms. In this case, we didn't need to. If you have more than 2 terms, you would have to group your like terms and then follow the order of operations to get to your answer. So note, to remove parentheses from an operation that follows a negative sign, imagine that the parentheses are preceded by a -1, and then you would use a distributive property. And this is what I was trying to tell you, I think maybe it was 2 or 3 lessons ago. And obviously it would have been confusing to you then because you didn't know this information. But hopefully this makes it clearer now, that anytime you see a negative sign in front of parentheses, you know that that negative sign carries across according to the distributive property. And you also know that there is an imaginary 1 here, as it tells us right here. Imagine that the parentheses are preceded by a 1. So rewriting that, we have a -1 times 2x plus 3. A -1 times 2x is a -2x. A -1 times 3 is a -3. So this expression right here can be rewritten as -2x minus 3. Okay, and again, all we're doing is, if we go back to our lesson on multiplication, we know that when you see 2 things written next to each other, it immediately implies multiplication, right? In this case, we don't have a number, we don't have a variable, we just have a negative sign. And so we have to think back to our distributive property, because this is just telling you that this negative sign needs to be distributed into everything that's in these parentheses. And you can imagine that there's a 1 here, because that 1 is not going to change the value of anything inside the parentheses, right? It just makes it easy for you to kind of keep track of what's going on with the negative sign. So you would just simply distribute the negative sign across the parentheses by multiplying the negative sign, or by multiplying everything inside the parentheses by the negative sign. So in this case, we have 2 terms inside the parentheses. That means that this negative sign is going to carry across, or going to be distributed to those 2 terms. This negative sign has to be distributed to 2x, and then it has to be distributed to 3. And so another way of writing this particular expression is -2x minus 3. Okay. Do you have any questions?
No.
Okay.
Nope. I'm good.
Okay. So more practice exercises, and I promise the more you work on these, the easier it'll get for you. The next portion of our lesson is on factors and multiples. And the key ideas to remember is that prime factorization of an integer are the prime numbers that can be multiplied together to equal that integer. So for example, an integer is a whole number, right? So if we had 4, for example, okay, that's a whole number or an integer. And then what are the factors or the numbers that can be multiplied together to give us 4? Well, 2 times 2, right? So 2 would be a prime factor of 4. And this is again where it's important to learn your multiplication table, so that this portion of the test will be easier for you to work through. So just Google multiplication table, and then go ahead and memorize them, or at least get familiar with them from 1 to 12. If you do that, not only will this portion of the test be easier, but all the other portions where you're having to divide things, because you can check yourself. Yeah. All
Okay.
right. The greatest common factor of two integers is the largest integer that will divide evenly into both, right? So again, back to our example with 4, the greatest common factor, okay, well, let's do 4 and 8. Okay, greatest common factor would be 4, because 4 would divide evenly into 4, and 4 into 8 is 2. The least common multiple of two integers is the smallest number that both integers will divide evenly into. So again, if we go into our, if we go with our example of 4 and 8, the least common multiple would be 2, because 2 goes into 4 twice, 2 goes into 8 4 times. It's the smallest number that can divide into both numbers evenly without leaving any remainders. All right. So when you multiply two numbers to create a product, the numbers you multiply are called factors. So the pairs of factors that can be multiplied to produce a whole number can easily be listed in something known as a T-chart. And this is an example of a T-chart. So in this example, we're being told to find factors of 10. So you would write 10 on top, and then you would go ahead and start by drawing your T first, and then list the factors. 1 goes into 10 exactly 10 times, right? Then you draw your line. What's the next factor? Well, 2 goes into 10 exactly 5 times. We can just simply add negative signs to our positive factor. -1 goes into 10, -10 times, right? Or 10 divided by -1 is -10. That's essentially what this means, right? 10 divided, or -2 goes into 10 -5 times, or 10 divided by -2 is -5. Right? And each time you can check yourself, you can check your answer to make sure that your factors are correct simply by multiplying your factor with whatever your answer is. So in this case, we said that 1 goes into 10 times. So this is our factor, this is our answer. 1 times 10 is 10. We said that 2 goes into 10 5 times, right? So this is our factor, this is what we found when we divided our factor into 10. 2 times 5 is 10. So we know that 2 is a correct factor of 10. -1 times -10 gives you 10, right? Because we said that -1 divided by 10 is -10. And if we go back to our lesson on signs, when you're dividing by a negative number, so we have a negative number here, -1, and we have a positive number, so our answer is going to be negative. And that's what we have here, -10. When you multiply two negative numbers together, you get a positive number, right? So -1 times -10 is 10. So we also know that -1 is a correct factor of 10. -2 into 10 is -5. -2 times -5 is 10. So we also know that -2 is indeed a correct factor of 10. So then you just simply count the number of factors that you have in a T-chart. In this case, it's 1, 2, -1, and -2. 10, 5, -10, and -5 are all factors, right? Because if we divided -5 into 10, we would get -2. If we divided -10 into 10, we would get -1. 5 into 10 is 2. 10 into 10 is 1, right? So you count all your factors, 1, 2, 3, 4, 5, 6, 7, 8. We have 8 factors in total. In order from least to greatest is -10, -5, -2, -1, 1, 2, 5, and 10. Okay. Again, if you were asked to pick out the least greatest factor, in this case, it would be -10. Why? Because -10, when you picture your number line, -10 is the furthest from 0, right? Because we're going -10, -9, -8, -7, on and on and on until you get to 0. So because it's the furthest from 0, it's the smallest. when you're on the negative side of the number line. Of course, 10 is the greatest. Why? Because it's the furthest from 0, but we are on the positive side of the number line, right? I mean, you know this already from everyday dealings, but I'm just making that point to emphasize that don't get tricked into thinking that -1 is the least because it's 1. No, -1 is actually greater than -10. Why? Because -1 is closest to 0 on the number line. Can treat the number line as key and the distance to 0 as your kingpin or the determinant. The 0 being the decision maker. Or you can think of it as you're back in your role as an accountant and you have a client that has a bank account balance of -10. You have another client that has a bank account balance of -1. Well, which one is quote unquote richer? The one that owes less, right? Which would be this guy that owes negative $1, right? So in that sense, -1 is greater because that guy that owes $1 is a lot quote unquote richer than the guy that owes $10, if that helps to think of it that way. Just keep in mind that when you're dealing with negative numbers, the further you are from 0 on the number line, the smaller the number. When you're on the left side, in terms of prime numbers are positive whole numbers with only 2 positive factors, 1 and the number itself. So examples of prime numbers are 2, 3, 5, 7, 11, and 13. And note that 1 is not a prime number because it only has 1 factor. Remember, a prime number is a whole number with 2 positive factors, 1 and itself. For example, 1 goes into 2 twice, 2 goes into itself 1 time, right? So you can divide 2 by 1 and you would get 2. You can divide 2 by 2 and you would get 1. That's all that means, like 1 and a number that goes into itself without any leftovers. Again, examples of prime numbers are 2, 3, 5, 7, 11, and 13. But these are all numbers that can only be divided by 1 and themselves. They can't be divided by anything else. Okay, I mean, they can, but you would have a number with a leftover. So the goal is to divide the number without having any leftovers. For example, 10 is not a prime number because, just as you discovered, it has 4 positive factors. It has 8 total factors, as we saw earlier, but remember our definition of prime numbers are positive whole numbers with only 2 positive factors, right? And so since 10 has 4 positive factors, it's not a prime number. However, the numbers 2 and 5 are prime numbers. Why? Because they're divisible by only 1 and themselves. Only positive factors of 2 are 1 and 2, and the only positive factors of 5 are 1 and 5. Thus, the prime factorization of 10 is 2 times 5. Okay, so don't get the two terminologies mixed up, right? We know that the factors of 10, there are 8 of them, and we went over them in the previous example. But the prime factorization of 10 is 2 and 5, right? Those are the only meaning of all those numbers that we found that are factors of 10. Only 2 and 5 meet this definition of prime number, right? They're the only 2 numbers that are divisible by 1 and themselves that are also factors of 10, right? And so that's what prime factorization means. So the prime factorization of 10 is 2 and 5. A number's prime factorization may include more than 2 factors, as in the next example. Again, don't get prime factorization confused with prime number. A prime number is divisible only by 1 and itself, but the prime factorization are those prime numbers that you can multiply together to give you a whole integer. Okay, so in this example, what is the prime factorization of 12? Well, you can break 12 into its prime factors. We know that 12 equals 4 times 3, and we can break down 4 further into 2 times 2. And so if you look at this string of numbers here, you know that these are prime numbers. Why? Because they're only divisible by 1 and themselves. And so now we have our prime factorization of 12. And why do we have our prime factorization of 12? Because we've broken down 12 into its prime numbers, okay? So 4 and 3 wouldn't be the prime factorization of 12. Why? Because 4 can be divided by 1, it can be divided by 2, and it can be divided by itself. That's 3 different factors, and that doesn't fit our definition of prime numbers. Why? Because a prime number can only have 2 positive factors, 1 and itself, right? So we break down 4 further, and so we now have our prime factorization of 12. 2 times 2 is 4, times 3 is 12. When you need to add or subtract fractions with different denominators, and the denominators are large, instead of multiplying the denominators to find a common denominator, you want to use the prime factorization to find their least common multiple. So prime factors can be used to find 2 values that may be useful in simplifying expressions and solving equations. The greatest common factor, or GCF, of 2 integers is the largest number that divides evenly into both integers. To find the greatest common factor, you want to break down both integers and into their prime factorizations. Find the prime factors they have in common, and then multiply those prime factors. This is handy when you're using the distributive property to rewrite 2 or more terms as 1. Okay, and we'll see examples of that coming up. So in this example, we're being asked, what is the greatest common factor? 40 and 140. So you want to begin, let me zoom in. And I went in with a marker to try to make this a little bit easier to follow, right? So you want to start by identifying the prime factors of each number, right? So we know that 40 is equal to 4 times 10. So we've broken down 40 a little bit so that it can help us identify the prime numbers associated with our factors of 40. So the prime numbers associated with 4 is 2. We know that 2 times 2 is 4, right? Prime numbers associated with 10, we've already established is 2 and 5, right? And so here we have our prime numbers, which are factors of 40. So we have our prime factorization of 40, 2 times 2 times 2 times 5. Then we do the same thing with 140, right? We break it down into the simplest terms that can be multiplied into each other first, right? In this case, 10 and 14. And then we find the factors of 10 and the factors of 14. So again, the factors of 10, prime factors of 10 are 2 and 5, and the prime factors of 14 are 2 and 7, right? And again, prime meaning they can only be divided by 1 and themselves, right? So 2 times 5 is 10, 2 times 7 is 14, 10 times 14 is 140. So we have our prime factorization of 140, okay? And then you're going to see what prime factors the 2 numbers have in common, right? Both integers share 2's and they share 1, 5, right? And I highlighted that so that it's easier to follow. We can see that they both share 2's, and they both share 5. So you want to multiply the common factors, or the factors that they both share. So the greatest common factor is 2 times 2 times 5, which is 20. And this is let me zoom out, be easier to read. This is the largest number that divides evenly into 40 and 140. So note that you can rewrite the expression 40 plus 140 as 20, and then open parentheses, 2 plus 7. Why? Because 20 times 2 is 40, plus 20 times 7, which is 140. Right? So 40 plus 140 can be rewritten in terms of its factors as 20 times 2 plus 7. Okay, and I think in further lessons you will see why this becomes important. But for now, know that the greatest common factor you can find by first identifying the prime factors of each number, and then you know, based on the greatest common factor that you found, which is 20, that you can rewrite 40 plus 140 based on the greatest common factor. Doing that, you would get 20, open parentheses, 2 plus 7. And again, if you multiply the greatest common factor by the prime numbers 2 and 7, you would get the expression 40 plus 140. Why? Because 20 times 2 is 40 and 20 times 7 is 140. Okay, there's just different ways of expressing the same set of numbers, basically. Okay, and I think that this will, once you memorize your multiplication table, this would be a lot easier to see. The least common multiple of two integers is the smallest number that both integers divide into. To find the least common multiple, you want to break down the integers into their prime factorizations. Select each prime factor the most number of times that it occurs, and then multiply all the factors that you have selected. And this will make sense in the example that follows. So what is the least common multiple of 20 and 30? Let me zoom in and make it easier to see. Again, you want to start by identifying the prime factors of each number. So we know that 20 is 4 times 5 based on our multiplication table, right? And we know that 4 can be broken down further into its prime factors, 2 times 2, and 5 is already a prime number that can't be broken down any further. So we have our prime factorization of 20. And then you do the same with 30. Based on your multiplication table, you know that 6 times 5 is 30, right? So looking at 6, we know that it can be broken down into prime numbers 2 and 3. 2 times 3 is 6. And 5 is already a prime number that we can't do much else with it. So we have our prime factorization of 30. 2 times 3 times 5. Okay, 2 times 3 is 6. 6 times 5 is 30. Again, this is where it's important for you to learn the multiplication table, because it makes it a lot easier for you to identify your prime numbers. In this example, because we know that 4 times 5 is 20, we can break down 4 into its 2 times 2, and we have our prime factorization. We know that 6 times 5 is 30. We can break down 6 into prime numbers, 2 times 3, and we have our prime factorization. 2 times 3 times 5 is equal to 30. Okay, so once you have your prime factorization done, then you want to select each factor the most number of times that it occurs. The factor 2 appears twice in 20, 2 times 2, so you select 2 times 2. The factor 3 appears once in 30, so you select 3. And then the factor 5 appears once in both 20 and 30, so you select 5. And then you would just multiply those factors together. So the least common multiple is 2 times 2 times 3 times 5, which is 60. And this is essentially the smallest number that both 20 and 30 can divide into without leaving any leftovers. 20 goes into 60 3 times, and 30 goes into 60 twice. If you needed to solve 7 over 20 plus 7 over 30, you would use the common denominator of 60. Remember from our lesson on fractions, you can't just simply add across, right? You would find the least common denominator or the least common multiple. In this case, that happens to be 60. And then you would rewrite both in terms of their least common multiples. So when I say in terms of their least common multiples, they now share a denominator of 60, right? Because we've gone through the exercise of finding the least common multiple of 20 and 30, we know that that's 60. So starting with your first term here, 7 over 20, we know that 20 goes into 60 3 times. 7 times 3 is 21. We know that 30 goes into 60 twice. So since we've changed the denominator to 60 by multiplying 30 by 2, we also need to do the same thing with the numerator. 7 times 2 is 14. And now you can add across. 21 plus 14 is 35. 35 over 60 is now your new fraction, or is the sum of 7 over 20 plus 7 over 30. And you can simplify this further by dividing by 5. We know that 7 times 5 is 35. So 5 goes into 35 7 times. We know that 12 times 5 is 60. So 5 goes into 60 12 times. So 7 over 12 is your lowest form of this sum, or the outcome of you adding your two fractions, 7 over 20 plus 7 over 30. So you can see how these principles kind of depend on and even work together. A lot of the stuff that we learned earlier on in the semester is coming together when working on these problems. Yeah, so that's essentially it for today. And again, just make sure that you're working on the practice exercises. And if you have any questions, definitely let me know.